Hello, this will be a demonstration of proposition 15 from book 3 of Euclid's Elements, which states that of the straight lines in a circle, the diameter is the greatest, and of the rest, the nearer to the center is greater than the more remote. What we are given then is the circle ABCD, like so. We have a diameter AD, like so. We have the center point E, like so. And also within the circle ABCD, we have the two straight lines. We're going to call this BC. We're going to call this other one FG. Not like that. On the other side. Well, not on the other side, but further away. Like that. Okay. We're going to call this FG. Now, what we are going to prove is that that of the straight lines in the circle, in this case we have three, AD, BC, and FG. AD is the greatest and will be greater than BC, and BC will be greater than FG. We also know that BC is nearer to the center E than FG is. Now, starting this proposition, from the point E, from the center E, we are going to draw EH perpendicular to BC, like so. And also from the center point E, we are going to draw EK perpendicular to FG, like so. Now from the definition of at a greater distance from the center, that's definition 3.5, we know that if a straight line be at a greater distance from the center than another straight line, then the perpendicular drawn to it from the center will be greater than the other. And so FG being at a greater distance from the center than BC, we know that its perpendicular EK will be greater than EH. Okay? Again, that's by definition 3.5. Now, because we know that EK is greater than EH, well, we can utilize proposition 1.3. And from EK, we can cut off the straight line EL such that it is equal to EH. That looks about right. So EL is going to be equal to EH. Now, from this point L, we are going to draw LM perpendicular to EK. That will look something like this. Then we are also going to produce ML downwards to E like that. You know, those are right angles. I'm going to erase that because the L just got completely lost. And finally, we're going to join these straight lines ME, EN, FE, and EG. Like that. We can do that all by postulate 1. Now we know that EH is equal to EL, right? Because we made EL such that it is equal to EH. And so we know that BC will be equal to MN because BC and MN are equally distant from the center if their perpendiculars, namely EH and EL, be equal. The two straight lines will be equally distant from the center. That's definition 3.4. And if they are equally distant from the center, we know by the previous proposition 3.14 that they will be equal. And so we can say that BC will be equal to MN, like so. Now we know that AE is equal to EM by definition 1.15. That radii in the same circle are equal to each other. We know by the same definition that ED is equal to EN. And so if we add these equals together, the sums that we will get will also be equal. That's common notion too. And so AE plus ED, that is the straight line AD. So if we add AE and ED like so, we get the whole straight line AD. So we can say that AD will be equal to EM plus EN. It's common notion 2 again. Now by proposition 120, that if two sides of a triangle be added together, they will be greater than the remaining side. We can say that ME plus EN is greater than MN. And by a property of magnitudes, we can substitute all these values out. We know that ME plus EN is equal to AD, and we know that MN is equal to BC, so that we can say that AD is greater than BC. Now, again, by definition 115, we know that ME is equal to FE. Where is that? Right here. And we also know that EN is equal to EG, again, by definition 115. And we also know that the angle MEN is greater than the angle FEG, because the angle FEG is a part of the angle MEN. That's common notion 5. So by Prop 124, that if in two triangles, two sides be equal to two sides, and the angle contained by the equal sides in the one be greater than the angle contained by the equal sides in the other, the base of the one will be greater than the base of the other. In this case, that means that MN, which is the base of the triangle MEN, which subtends the angle MEN, is greater than FG, which is the base of the triangle FEG, which subtends the angle FEG. So we can say that MN is greater than FG. Excuse me. Now, we know that, I got lost. We can substitute MN for its equal, that is BC, so that we can say that BC is greater than FG. And combining all these inequalities together, we can say that AD is greater than BC is greater than FG. This being what we set out to prove, we are done with the proposition, therefore, etc., QED. I have nothing to say about this proposition, so I shall move on to 316.